Europe, Asia, and the Middle East, highlighting the profound impact solar activity can have on our technology-dependent world. In this video, we'll explore the nature of this solar flare, its immediate effects on Earth, and the broader implications for our planet's infrastructure and preparedness. X 2.7 class solar flare that erupted on May 14, 2025, stands as the most intense solar event of the year. Originating from Sunspot region AR 4087, this flare peaked at 0825 UTC, releasing a massive burst of energy that traveled at the speed of light, impacting Earth's upper atmosphere almost instantaneously. Solar flares are categorized based on their X-ray brightness in the wavelength range of 1 to 8 angstroms. The classes A, B, C, M, and X represent increasing orders of magnitude, with each class being 10 times more powerful than the previous. An X-class flare, therefore, is the most potent, and the number following the class indicates its strength. An X 2.7 flare is thus 2.7 times more intense than an X 1.0 flare. Sunspot region AR 4087 had already shown signs of heightened activity prior to this event. On May 13th, it produced an X 1.2 class flare, followed by an M 5.3 class flare earlier on May 14th. These successive flares indicate a highly active region on the Sun's surface, capable of producing significant solar storms. The X 2.7 flare's rapid release of X-rays and extreme ultraviolet radiation ionize the Earth's upper atmosphere, particularly affecting the ionosphere's D layer. This sudden ionization disrupted high-frequency HF radio communications on the sunlit side of the planet, leading to widespread radio blackouts. While the flare itself did not produce a coronal mass ejection, CME, directed at Earth, the potential for future CMEs from active region 4087 remains a concern. As this sunspot region rotates to face Earth more directly, the likelihood of Earth-directed CMEs increases, which could have more severe geomagnetic consequences. The immediate aftermath of the X 2.7 solar flare was felt across multiple continents. High-frequency radio blackouts were reported in Europe, Asia, and the Middle East, affecting aviation, maritime operations, and emergency communications. These disruptions underscore the vulnerability of our communication systems to space weather events. The flare's impact on the ionosphere led to increased absorption of HF radio waves, particularly in the 3 to 30 MHz range. This absorption rendered HF radio communication unreliable or completely inoperative in affected regions, posing challenges for industries and services that rely on these frequencies for long-distance communication. Beyond communication disruptions, solar flares can affect satellite operations and navigation systems. Increased ionization can lead to signal delays or loss in global navigation satellite systems, GNSS, impacting GPS accuracy. Satellites in low Earth orbit may also experience increased drag due to atmospheric expansion, potentially altering their trajectories. While the May 14th flare did not produce a significant CME, the potential for future CMEs from active region 4087 remains. CMEs can induce geomagnetic storms upon interacting with Earth's magnetic field, leading to power grid failures, pipeline corrosion, and increased radiation exposure for high-altitude flights and astronauts. The cumulative effect of these disruptions highlights the importance of monitoring solar activity and developing resilient infrastructure to mitigate the impacts of space weather events. Recent solar flare activity is a stark reminder of the Sun's immense power and its unpredictable influence on our technologically dependent world. As we edge closer to the peak of solar cycle 25, expected sometime around late 2025, scientists are closely monitoring a sharp uptick in the frequency and intensity of solar eruptions. These flares, especially of the X-class variety, are becoming more common and impactful. Over the last 2 years, the Sun has been particularly restless, providing a dramatic prelude to the solar maximum. In 2024, Sunspot region AR 3664 unleashed an X 8.7 class flare on May 14th, the largest of that year and one of the strongest in decades. This event triggered a rare G5 class geomagnetic storm, a level not seen since the infamous 2003 Halloween storms. The result? Brilliant auroras lit up skies as far south as Texas and Spain. GPS and radio signals were thrown into disarray, and aviation routes had to be temporarily restructured. That was only the beginning. On February 22, 2024, another intense X 6.3 flare erupted, followed by an X 9.0 monster flare on October 3rd. Although Earth wasn't hit directly by all the resulting coronal mass ejections, CMEs, the sheer power of these bursts highlighted the chaotic nature of our Sun during its active cycle. Scientists and space agencies have since issued repeated advisories, stressing the urgency of preparedness as more X-class flares are likely to emerge. Fast forward to 2025, and the activity has continued. Prior to the X 2.7 flare from Sunspot AR4087 on May 14th, we witnessed an X 1.2 flare from the same region just a day earlier, followed by an M 5.3 class flare in the same 24-hour period. These successive bursts aren't isolated incidents. They're indicative of an underlying solar storm brewing on the surface of the sun. Experts warned that AR4087 still holds the potential to release more powerful CMEs, especially as it continues to rotate more directly toward Earth. This rising activity emphasizes the critical need to understand, forecast, and prepare for space weather events. Agencies such as NASA, ESA, and NOAA's Space Weather Prediction Center have intensified monitoring of solar behavior using space-based observatories like the Solar Dynamics Observatory, SDO, and the Parker Solar Probe. These missions are designed not only to observe the sun's outer atmosphere, but to help scientists predict solar flare patterns and alert Earth in advance of any dangerous CME impact. While solar flares themselves strike Earth almost instantaneously, traveling at the speed of light, CMEs take longer, typically several hours to days. This delay provides a crucial window for early warning systems to alert satellite operators, airlines, and grid managers. However, not all flares are accompanied by CMEs, and not all CMEs are Earth-directed. Predicting them still remains one of space weather forecasting's most complex challenges. Investments in space weather resilience are therefore becoming essential. Modern infrastructure, especially satellites, aviation systems, military communications, and power grids, are increasingly vulnerable to solar disturbances. Strategies for hardening satellites with better shielding, reinforcing transformer substations in electric grids, and building redundancy into global positioning systems are actively being explored by governments and private sector stakeholders alike. But technology alone is not enough. Raising public awareness and educational outreach about space weather is equally important. As with hurricanes or earthquakes, understanding the science behind solar flares can empower people and organizations to act swiftly and wisely during disruptions. For example, pilots and airline crews receive special briefings during heightened solar storm periods to avoid polar routes that are more exposed to solar radiation. In conclusion, the X 2.7 flare on May 14th, 2025 is more than a solar headline. It's a critical data point in a growing chain of powerful solar events marking this solar cycle. It reminds us that the sun is not just a distant star warming our planet. It is a volatile, living sphere capable of shaking Earth's technological foundations in an instant. As we progress deeper into 2025 and approach the climax of Solar Cycle 25, a coordinated global effort to monitor, model, and prepare for these space weather events will be essential to safeguard both our technology and our future. Thank you for watching. Stay informed and prepared as we continue to explore the dynamic relationship between our planet and the sun.